Welcome to EDU World Space.
So in this problem, there are no external forces, and hence momentum is conserved. So in a diagram, we can see the initial momentum is due to disk A, and that's ma times its velocity v0. The other three disks, C, B, and D, are all stationary, and hence their momentum is 0. The final momentum for ball C is mc vc after the collision. Disk A and B move together and have momentum ma plus mb times their common velocity vb. And disk D moves to the right as well with momentum md times vd. So we are given va and vb. We need to calculate vc and vd. We are also given v0. So the first thing we'll do is we will take moments, we'll take clockwise moments about d. So taking clockwise moments about d gives us the following: 3 times the initial momentum, which is ma v0, is equal to 6 mc vc plus 3 into ma plus mb into vb. So taking moments about d gives us this expression. And if we rearrange this expression and make vc the subject of the formula, we get the speed of c, vc, is equal to 3 times ma over 6 times mc times v0 minus 3 into ma plus mb all over 6 mc times vb. So now we have vc in terms of v0 and vb, and both these speeds are known, so we can substitute our values and find vc. So this turns out to be 0.5 into 38.5 minus the second term simplifies to 8.25, and hence we get the speed of c after the collision, vc, is 11 feet per second. So we have the speed for c, vc. Now to do the same for d, we will take anti-clockwise moments about c. So taking anti-clockwise moments about point c, we get that 3 times the initial momentum ma v0 is equal to 3 multiplied by the momentum of a and b, which is ma plus mb times vb plus 6 times the momentum of d, 6 md vd. And we do what we did before and make vd the subject of the formula. So vd is equal to 3 ma times v0. So that's, write this a bit clearly, this is 3 ma v0 over 6 md. Remember, all the masses of the disks are known, minus 3 into ma plus mb over 6 md multiplied by speed of disk B, vb. And if we substitute our values in here, again all these values are known. we get 0.25 into 38.5 minus 0.5 into 8.25. And hence we get the speed for disk D, Vd, to be 5.5 feet per second. So as required, we've solved for the speed of disk C and the speed of disk D after the collision. Now for part B, we want to calculate how much energy is lost in the collision. So firstly, we'll calculate the initial kinetic energy of the system. The initial kinetic energy is simply T1 due to disk A, and that's a half mv squared. That's a half times the weight of A over the gravitational acceleration G, which gives the mass of A, times V naught squared. And this is a half times the weight, which is 15 pounds, over 32.2 feet per square second. And we know V naught squared to be 38.5, that's squared. So we get the initial kinetic energy, which is only due to disk A, to be 345.24 foot-pounds. So that's our initial kinetic energy. Now let's calculate our final kinetic energy and see if we get the same answer. So the final kinetic energy, T2, is equal to the kinetic energy for each component of the system. So that's a half into the mass of A and B together, which is their weights, over G, times Vb squared, they move off with speed Vb, plus a half times the weight of C over G multiplied by the square of its velocity, Vc squared, plus a half Wd over G times Vd squared. That's a contribution to the final kinetic energy. And if we substitute our values in there again, since all these values are known, we get 73.98 foot-pounds. So again, all these values are known, and we've calculated Vc and Vd above. So we substitute them in this equation, and we get the final kinetic energy of the system to be 73.98 foot-pounds. So the energy that was lost is equal to the initial kinetic energy, 345.24 minus 73.98. And so the lost energy is equivalent to 271.26, and that's foot-pounds. So the fraction of energy that is lost is equal to, so the fraction of energy that is lost is 271.26 over the initial kinetic energy, 345.24. And that's a fraction of 0.786, or 78.6% of the initial kinetic energy is lost.